Gentlemen, welcome back. All right, good morning. Welcome back. Hopefully you guys are doing well and staying safe. Looking for a couple people here today. I'm looking for Alex, Leonardo, Joseph. That's it. If you guys are here, please let me know. Please put your name in the chat or unmute yourself. Just say, hey, Mr. Brown, I'm here. All right, a couple things for housekeeping. Sorry I was not here on Friday. You guys had the day off. You had an assignment to complete, but I had to take my son to an appointment and just couldn't work with the time of after school, all that stuff. And also I had some people doing some stuff to my house. So sorry I was not here. I do not like to take time off, but I did for that reason. Moving on forward. Hi, Leo. Try to get here a couple minutes earlier, please. Moving on forward, what happened on that Friday? You had to do an assignment on review from unit number 7, Kinetics and Equilibrium. We'll start off class by going through that. We'll go through some odd questions there, and then we'll move on forward and obviously do the agenda too. So that's the goal for today. But before we do that, let's go through some housekeeping here. Let's check out the COVID numbers for Oneida County and see where the numbers stand. Oneida County, we have 439 active cases of COVID in the county. Resolved cases, there's 19,067 resolved cases. Total number of deaths, there's 401 deaths. So another death was added to the death toll. Hopefully it was no one close to you. Number of people in the hospitals, you can see there's 27 people in the hospital and 4 people in ICU. Number of vaccines, it keeps getting bigger and bigger and bigger. Good. Hopefully we vaccinate more and more people. Moving on, number of daily positive cases. Full year of the pandemic. Crazy. And the last few days of data, let's just check them out. Last few days of data, you can see 20 on the 14th. Good data there. Hopefully you can repeat that data all week. The 13th, there are 38. Day before that, 12th, there's 30. Day before that, there's 32. Day before that, there's 44. And the 9th, there's 33. So looks, for the most part, for the most part, that's a pretty even line there. You could check it out. And it looks like it's averaged out relatively flat for the most part. With a couple little low days, a couple high days. But for the most part, it was a pretty good week for COVID numbers. Hopefully, we get down below 30 this week. That's a nice goal for us. So for below 30 all week, and next week maybe below 20, things are going to look better and better and better for us. But additionally, on Friday, there was a staff meeting, which I did attend. And within that staff meeting, they talked about some rollback procedures for when students come back to Proctor. No date yet. There's no date yet. But what's going to happen, you guys know you're going to be split into 5 different groups. This week, I should have a roster of who's in which cohort for at least my class. I'm not going to know your entire schedule of how many people are in your classes, but for my class, I'll be able to know how many students are coming on a given day or maximum number of students on a given day. You know you're split into 5 different cohorts, 5 different groups. And I think the first time I really talked about this, maybe I talked about this and said, hey, if we're cohort A, you're coming on Monday. Cohort B is on Tuesday. C is on Wednesday, so on and so forth. That is no longer the plan. It's no longer the plan that, hey, for cohort A or cohort 1, whatever they're going to call it, it no longer means you're coming on a specific day. If we're in cohort A, you could come on day 1, day 2, day 3, day 4, whatever it is. So what's going to happen at Proctor? Let me let Alex in here. That's got a late pass, hopefully. Or should I lock him out? Hey, I'll try to get here 7 minutes earlier, please, for next time. So what's going to happen when you come to Proctor? Oh, whatever cohort you're in doesn't mean the specific day. What's going to happen at Proctor is there going to be cycle days. Days 1, 2, 3, 4. Repeat. 1, 2, 3, 4. Repeat. 1, 2, 3, 4. And what's going to happen? You're going to be A is going to go on a certain day. It's just going to follow that cycle. You're following that cycle through. It's not corresponding to the day of the week. So whenever that cycle's done for the cohorts, it goes back to the beginning. But you should get some more literature or more information on that as soon as they make it board approved. So it's no longer cohort B comes on Tuesday. It's just going to keep cycling. Hopefully you guys kind of understand what I'm trying to say there. Yes. Still some questions there. No problem. So we have Monday. Let's just look at a calendar. Monday, Tuesday, Wednesday, Thursday, Friday. What happens, there's day 1 on Monday. Day 2 would be Wednesday. Day 3, 4, and then back to the top again. Then it's 1. Then it's going to be 2, 3, 4, 1, 2, whatever. So what's going to happen, whatever, it's going to start off with cohort A probably coming on the first day. Then B is going to come on the second day. C, D, and then cohort E would come on the day 1. Then it goes back to the top again. A, B, C, D, E. Then next week, you can obviously see whatever it's going to be. I'm sure they'll give you something similar to this. That Monday is going to be day 3, day 4, 1, 2, 3. I think this will clear it up a little bit. So it's going to be this type of system where it's going to be rolled back. Yes, but it's not going to always be the same day. As long as there's 5 days in a week, it'll be coming back once, 1 day per week, unless they change it again. Oh, yeah. Yeah. So what's going to happen sometimes is the days are going to get shifted a little bit. So maybe there's no school on a certain day. A, B, C, I'm sorry, distracted by a couple things. E. But maybe there's no school on this Monday coming up. So there's no school on this Monday, whatever it is. So what's going to happen, it's going to shift around a little bit. So the schedule is going to shift. So now day Tuesday, so the next day you come back, this is a day 4. This would be a day 1. This would be day 2. Let's say there's no school on that Friday, 2. There's no school on that Friday. No school there. So what's going to happen? B, C, D, E. This is going to be day A. Group A would come this day. Group B would come this day. C. I think you guys know where I'm rolling with this. So it shifts the days a little bit. I know, yeah, it looks like right here. Definitely looks like this, where they come, each group comes on a certain day, but don't always think about you come on a given Monday because you're cohort A, because it could shift. Days off from school on a Monday doesn't really work out that way. Why do they do that? Because if there's like several Fridays where you're not going to be in school, then they don't want the students that come on Friday to not miss out or have that opportunity to come back. So we're going back once a week, most likely once a week if there's 5 days. Supposedly, each of the classrooms that you're going to be in are going to be 6 feet apart for your desks. There's going to be sanitizer. There's going to be alcohol wipes. There's going to be some cleaner in the room as well with some paper towels. And there's also going to be Chromebooks in there too. So supposedly all the rooms will have all that happening. It should be a safe environment. I walked in the hallways today and they're putting out like little stickers, like one-way street stickers on the floor. So they know that, hey, if you walk one way, you're going this direction, the opposite way on the other side of the hallway in an opposite direction. So it should be a pretty safe environment. I feel safe around here. You'll wear your mask in your classrooms. So you'll see me with a mask on teaching. But again, I'll be teaching to you guys on the screen, my majority population on the screen, but I'll also teach to the people that are in front of me as well. When I do breakout rooms, I'll probably give them more attention to people in front of me. Instead of maybe, I'll probably walk away from the screen at that period. Additional information that I have for you. One more question here. The cohorts, if you're in cohort A's, it does not always mean you come on day 1. If they broke it up into 4 different groups, that would make a lot more sense, but it can't work out. It's not going to work out that way. So hopefully that helps with that. you need more help with that, whoever asked that question, feel free to ask, and I'll try to go through it. But again, it has not been approved yet, and we don't know a date to when we'll return. It's going to happen. I don't know when, but it's going to happen. Additional information from that little meeting I had is if you're a walker, if you walk to school, or you get dropped off to school, you're going to go to the main entrance in the older building, and they're going to walk in that way. You're going to give you a breakfast. You can have your breakfast in the ROTC room, and then they'll have you guys hang out in there at social distance until 7:55. If you get bused to school, you're going to be dropped off at the Arcuri entrance. They'll give you your lunch. You'll head up to the lunchroom, and you'll hang out in there until 7:55. Once 7:55 hits, you're going to notice that the population is going to be a lot smaller at Proctor. There's only going to be like 500 or so people in the school. And you're going to be smart. You'll head over to your classes. You follow the same routine throughout the day. So whatever your schedule says, that's what you're going to do. That's what you're going to follow, whatever day that is. If it's obviously a day 3, you don't have chemistry class, you go to whatever is on your schedule, whether it be study hall, whether it be phys ed, whether it be ROTC. You follow that schedule however it says. You guys asked, what about lunches? Are we eating lunches in the classroom? No. I asked that question at the meeting. They said lunches will be served in the cafeteria, and the janitors have been working on separating like all tables, desk, all that stuff throughout the cafeteria. So the plan is to have lunches in the cafeteria with a smaller population. They're still planning on spring sports. That's a good sign. And it will definitely be safe. So I think it would be a good idea for you guys with numbers. We watched numbers since the beginning of the year. We saw that big increase. We were looking at the lower part of the curve. But I think it'd be a pretty good idea for you to get out of your house at least once a week, just to start and see what Proctor's like. Spend your 10th grade year coming to Proctor 10 times throughout the year. It's going to be different, but it's good to get out and just get a little bit more exposure to what's going on at school. Again, that's your decision. It's going to be your parents' decision and your decision whether or not you want to come back or continue with that virtual learning. My routine in my class, just so you're aware, is going to be very similar to what I'm doing now. I have 27 people on right now. I'll probably have 6, maybe less, 5, 4 people in my class. I'm not going to abandon the other 20 people that are hanging out virtually. So my plan will be very similar. I'll have Chromebooks in here. I'll have the smartboard TV linked in, ready to roll, and you'll be able to engage either just by looking at me or through the computer screen. If you want to take your notes, paper and pen, you'll have the option. I'll have that provided for you if you want to. If you miss writing with a paper and pen, which I do, if you miss that, then I'll have that for you as well. More things. You guys probably read that the regents for chemistry, physics, and the other electives have been slated for this year, canceled for this year. That came out yesterday. There's 4 regencies right now that are offered. It's going to be Earth Science, Living Environment, Biology. It's going to be English and 1 Math. That's what's going to be offered for the year. Right now, could change, but right now they said they canceled the extra regencies or the higher level regencies that are offered. So that includes chemistry, a lot of history, and obviously physics as well. So there's a handful of regencies that are canceled for this year. Stinks. I know it stinks because we're already on unit number 8. We're going to be on unit 8 today. And I know you want to express your knowledge of this course, and I want you to see what you retain throughout the year, but I guess we're going to have to do it a different way. We'll do it with a final exam instead. So I'm still going to do my job. I'm still going to teach the content because you never know. Some of you guys might need chemistry for college. And I want you guys to be prepared. I'm going to pray the best I can do as possible to get you ready for the next stage of your life. Some of you guys are going to be pharmacists. Some of you guys are going to be nurses. Some of you guys are going to go on to be engineers or doctors. You're going to need chemistry. I'm doing my job so you can be prepared in the future. I don't know about credits. I don't officially, my administration didn't tell me that the Regents are canceled. So I'm going to pretend that the Regents are still going today until they tell me otherwise. Other people are commenting in. Yeah, you can definitely take paper and pen for the class when you come in if you want to. I don't care. You can even take a paper and pen. You can take those notes in style at home. If you want to print out a copy of the notes, copy them down with paper and pen, you could do that. But you have to upload all those so I can see that you did your notes too. Yeah, I think you're right, Faith, with the ones that are still on. And I don't know about credit. Someone asked about that. But as long as you guys are working, which most of you guys are, you'll continue to do well in this class. Any other questions for me that I could try to address or find some answers or maybe answer myself? Anything else you want to know that I could ask in a future meeting? That I missed maybe, or something else? I don't have a date. They'll come from somebody higher up than I. It was just in the paper. It was just not the paper. It was just announced yesterday. Oh, good question. Good questions there. Good question, Faith. Faith asked, are we allowed to bring our own personal laptops in? If you're given a laptop from the school, if you're given a Chromebook from the school, they said you cannot bring that in. You cannot use that, which I won't give you my opinion on that. But if you have your own Chromebook from the school, they said you cannot use that in the building because your parents signed a waiver saying that they're responsible for it. And what happens during the school day, if your son or daughter lost the Chromebook, then how are they responsible when, I don't know. But you can't use your own Chromebook if you're borrowed from school. I don't know about your own device because your own device can have a hard time connecting to the network. I'll ask that. Is there a way that students could use your own device while in school? Maybe, I don't know. I'll get back to you on that one. Will we have lockers? I'm going to guess no on that one, but I'll ask that. Regents are so far. Oh, additional regencies? Someone asked, are we taking regents at school or online? I'm guessing that's for the additional regencies for English. I don't know if that's out there yet. That is the question a lot of teachers are asking. I'll figure that one out. All right, I think I have the questions that you guys are still asking. I'll try to, I'll ask them at the next meeting and see if I get the answers. They might not know some of these questions, so we'll get back to you when I can. If you have more questions, feel free to throw them in the chat. I'll overview them at the end of class too. All right, here we go. Moving on forward, let's go through the agenda for today. I didn't update this quote yet. Okay, Tuesday, March 16th, 2021. Today's a day 4. We're continuing on, and we'll finish up kinetics and equilibrium today. We'll go through topic 5, which is entropy and enthalpy. We'll define those two terms. We'll watch a YouTube flick on entropy. We'll hammer out the notes. It's not a big portion of notes for the topic. And then actually we'll not play that video. You can watch that one if you want to at the end of class. But I will go through these examples on entropy and enthalpy. Super simple questions if you know these two terms. But before we do that, let's review the odd questions from the last day of class. Some of you guys didn't finish it. 10 of you guys did not submit your work yet. So again, another piece of information to throw out there to you guys is your benchmark exam will be at the end of the month. What's going to be on the benchmark exam? It's going to be Unit 6, which is Properties of Solution, the last unit. Unit 7, which is Kinetics and Equilibrium. And it's also going to be Unit number 2, which is Matter and Energy.
So we're at a good place right now. We have a good pace of where we should be throughout the year. Do not forget you will have a benchmark on Unit 2, Matter and Energy, Unit number 6, which is Properties of Solutions, and obviously this unit as well. I'm definitely not going to stop and just review just those 3 units for the benchmark from now to then. I will be moving forward tomorrow with a different unit. So benchmark exam is only for quarter number 3, not the entire year. All right, so I will do these odd questions. I'm going to hammer them out quickly, and we'll move on forward. Question number 1, as the temperature increases, the number of affected collisions between particles in a chemical reaction. So temperature increases. There's 4 factors that affect the rate of reaction. Increase in temp, or temperature, pressure on gases, surface area, and concentration. 4 factors that affect the rate of reaction. If you increase the temp, what happens? There's more affected collisions. So temperature increases, there's more affected collisions. What's an affected collision? It has to be oriented correctly, and it has to have enough speed. Temperature increase, what happens? Particles move faster, faster, faster. So it's going to increase only. Increase is not going to decrease. As long as temperature continues to increase, the affected collisions will increase too. Number 3, I'm doing the odd questions. Which change would most likely increase the rate of a chemical reaction? Decreasing a concentration is going to slow down the rate of reaction. Decreasing the surface area slows down the rate of reaction. Cooling or lowering the temperature decreases the rate of reaction. Adding a catalyst to a mixture, catalyst is something that speeds up the rate of reaction. That is going to be something that increases the rate of reaction. Best answer, D for number 3. Next up, number 5. Raising the temperature speeds up the rate of a chemical reaction by another temperature question. Temperature increases. What happens? There's more effective collisions. Frequency of the collisions, how often they're going to collide. That's going to happen too. So you have more affected collisions, or you have more collisions as well. The frequency or how many collisions are happening, that's going to be affected too. Number 5, the best answer would be choice C. So again, this is good review for the unit. It's also good review for the benchmark. Number 7, odd questions. Which statement best explains the role of a catalyst in a chemical reaction? A catalyst is something that speeds up the rate of reaction. Why? Here's let's go with exothermic reaction, potential energy diagram. You have my reactants, you have the products, not my products. This is my PE of the reactants. This would be PE, potential energy of the product. Next interval, let's go a different color here. Activation energy is the energy needed to start the reaction on an angle. Shouldn't be an angle. So activation energy is that interval right there. Complex, the top of the peak to the bottom. The heat of the reaction we should be aware of goes from the reactant to the product. And the addition of a catalyst, I'll do in a yellow font. What happens with the catalyst? My reactants are the same, and so are my products the same. They're both the same. What's going to happen to a catalyst is it's going to go through the reaction, but it's not going to get as high of a complex, or it's not going to need as much activation energy. So those intervals will be reduced. What happens in a catalyst? A catalyst provides an alternate reaction pathway that requires less activation energy. Best answer, choice D. 7, best answer is D. Number 9, interval B represents the what? So B, this interval from the reactant, we kind of just went through this already, from the reactant to the top of the peak. Interval B is going to be best represented as the activation energy. Interval C, that interval is complicated. It goes to the top of the peak all the way to the bottom. Interval C represents the complex. Next up, interval G would be PE of the product. And last interval E would be PE of the reactant. Interval B is going to have to be activation energy. Try C for number 9. 9 is C. 9 is C. That's an endothermic reaction. Heat is absorbed. Energy is absorbed. Number 9, question. Which diagram represents potential energy of an exothermic reaction? Exo means to release, to leave. Thermic is referring to heat. Which one represents heat being released? You should be able to look at these curves and say, hey, B looks crazy. You never see anything like that. Definitely not. You didn't draw anything like that. And C would represent a reactant going through an energy, but not having enough energy to go through and produce a product. So it goes to the same levels from reactant, that's going to form a reactant again. It's not going to proceed to the product side of the reaction. It's not going to be C. Checking this out, you're looking for exothermic reaction. I told you, think of a building, and you're on top of the building.
My internet kicked me out. I'm sorry.
Sorry, no problem. You're on top of the building, and what's going to happen? There's a fire in the building. If there's a fire in the building, you're going to say, get the heck out of there. You're escaping. Exothermic reaction is going to be choice D. Exothermic reaction D. A would be endothermic reaction. So 11, best answer would be D. 13, we're doing the odd still. Consider the reaction. Which phrase best describes this reaction? The first thing I would do is find the energy. Find the energy, there it is. It's on the reactant side of the equation. Reactant to product. Energy's on the left. Anytime my energy or heat's kilojoules, energy's on the left, it's going to be absorbing, or it's going to be, let's rewind. Anytime it's on the left, it's going to be endothermic reaction. And what term goes with endo? Endo means inside, or endo means absorbing. So those terms are correctly aligned. Exo means to release. So those terms are correctly aligned. So it's got to be either A or D. Exo does not mean absorb. Endo does not mean releasing. Heat is on the left. It's got to be an endothermic reaction. Choice D is the best answer for number 13. 13 is D. Next up, 15. Which statement describes the characteristic of an endothermic reaction? Endothermic reaction, positive or negative. To find this, I look at the reference table. We'll get to the periodic table again tomorrow. We looked at table I. You guys told me the heat, types of reactions, endo, exothermic. You filled out that chart. But anyways, on this chart, it says a minus sign indicates an exothermic reaction. So again, minus sign indicates exothermic reaction. There's minus, exo, exo, exo. All the positive signs are going to indicate endothermic reaction. So positive signs for delta H. That's delta H value. You can see that at the top. Whoops, way too far. Delta H has got to be a positive value. Has to be a positive. So it's got to be A or B. And now it's talking about the products and the reactants. You have a potential energy diagram, rates of reaction, potential energy. It's talking about endothermic, so hopefully you could recall what an endothermic reaction looks like. There's a reactant, there's a product, and the product has more potential energy than the reactant. Products have more potential energy than the reactant. P is on the y-axis, potential energy. It's got to be choice B. 15 is B. Easy. Easy stuff so far, hopefully. Next up, number 17, talking about delta H. What does delta H mean? That's the change in heat, the heat of the reaction. That delta sign we saw earlier throughout the year. That delta H, heat energy, you see that triangle means change in. So the Greeks came up with this symbol, change, because you start at the beginning, you hit a corner, which is going to be a change in direction. another corner of the triangle, big change in direction. So change is going to mean difference. It's got to be difference. You saw change earlier throughout the year with change in temp. The formula was not equals. Q equals MC delta T. And you told me delta T meant temp final minus temp initial. Anytime it's temp or change in, it's going to be the final product, which is going to be the product, minus the heat of the reactants. Reactant, product, first, second, second, first. Always going to be second, first. That formula, delta, you'll know it in physics as well. You see that a lot. So it's got to be choice A for number 17. 17, best answer would have been choice A. 18, I'm going to give everybody a point for this question. It's giving the wrong table to check out. And these other compounds are actually not on that table. So I will give you a point for number 18 for whatever you put. Number 19, which phrase describes this reaction? Checking it out, look for heat, find, locate the heat. Heat's on the right side. There's your heat. Heat's on the right side. It has to be exo. Now you're saying, hey, Mr. Brown, what's the heat? Heat's 16,040 kilojoules. All right. But then you're like, is it positive or negative? Check out that table. You say delta H for an exothermic reaction has to be a negative value. So it's going to be a negative 1640 kilojoules. I know it looks a little confusing there, but it's going to be choice D for number 19. Negative delta H is going to be exothermic reaction. Moving on forward, number 21, talking about equilibrium in a closed system is shown in the diagram. The rate of formation of equilibrium is what? From a liquid to a gas, and from a gas to a liquid. Equilibrium, the rates are going to be equal. The rate of formation from liquid to gas, gas to liquid are going to be equal. Concentration different, rates are equal. 21, best answer is choice C. And 23. Le Chatelier analyzed the stresses on systems. What did he do? He stressed out closed containers by manipulating pressure on gases, temperature, and concentration. So he took those three things, he stressed the heck out of chemical reactions to figure out how they would react. Which one causes equilibrium to shift? All right, first one up, increase in pressure. Pressure only affects gases. There are no gases here. A is not going to be affected. Pressure is not going to be affected in this situation. Increasing temp. Temperature gets bigger, causes a shift to the opposite side. When something gets larger, it causes a shift to the opposite side. Looks like a good choice. Noble gas, if we throw like neon in here, which is non-reactive, it has 8 valence electrons, it's not going to cause a shift. It's not going to react to this reaction at all. It's going to be a loner. It's going to be all by itself. Not going to affect it. Adding a catalyst situation speeds up the rate of reaction, but it's not going to cause a shift to gain something else. So choice B, the best answer for 23. 25, next up. Equilibrium expression, which change causes a shift to the right. This time we want this equation to shift to the right side. Adding a catalyst speeds up the rate of reaction. Vague. Not going to tell you if it's going to shift to the right or left. Adding more O2. Let's check it out. You add some more O2. What happens here? O2 is going to be increased. Adding more O2. O2 goes from maybe 1 molarity to maybe 10. As this gets bigger, it causes a shift to the opposite side. So it looks like this will shift to the right. Let's check another one out. Decreasing pressure. If you decrease the pressure, it decreases the rate of reaction. So if the pressure decreases, the reaction is going to stay on this side. It's not going to proceed to the opposite side. It's going to take longer for the effective collisions. It's going to stay over here a little bit longer. Pressure decreases, the rate of reaction is going to slow down. Increase the temp. If we increase the temp, so that's going to increase. Let's put the arrow here. As temperature increases, heat increases, it causes a shift to the opposite side. What's going to happen? It causes a shift to the left. Best answer for 25 is going to be choice B. Choice B. Shift to the right, choice B. Le Chatelier. Number 27. Talking about another stress. Which stress would cause equilibrium to shift to the left? What's the opposite here? Stress. Shift to the left. Increase the temp. Check it out again. Temperature increases. Find temperature. Find energy. Find heat. Whatever it may be. There's your temperature. It goes from 22 to 44. Whatever. That increases. It causes a shift to the opposite side. Think about that process. Temperature increases. There's more effective collisions. Here, it's going to want to balance off. It's going to go to the other side a little bit quicker. So shifting to the left. Let's check another one. Increase in pressure. What's going to happen with pressure? Pressure is going to affect these gas particles a little bit more. We change the color here. These gas particles are going to be affected. Pressure's increased. There's two gases on the left. It's going to cause a shift to the right. Pressure increase is going to make these two things react quicker. Yeah, there's a gas there too, but the side where there's more particles is going to affect it more. Adding more N2. So this is going to be a shift to the right. Let's go to the next one. We said temp was a shift to the left. Let's add some more N2. Adding more N2 to the system. This increases, causes a shift to the opposite side. As something gets bigger, causes a shift to the opposite side. And last one, adding H2 to the system. Similar situation with H2. If I erase it, there it is. H2. H gets bigger, it causes a shift to the opposite side. This is going to shift to the right. Shift to the left is going to be choice A. Le Chatelier's principle. Stresses on systems. Last question, 29. The temperature of nitrogen gas is a measure of molecules average. So it's defining temperature. Temperature is the average kinetic energy of particles. Temperature is the average kinetic energy of particles. Choice C. Temperature, average kinetic energy of particles. No temperature. All right, so there's a little preview or review of kinetics. Hopefully you guys did that. Hopefully you did all the even questions too. Does anybody have any questions on anything before I move on? Is there an even question you got stuck on you want to check out, or are we good? Please make sure you submit this work. I think I had the due date Saturday, but I'll make it due this Saturday. I'll take it till this Saturday if you didn't turn it in yet. All right, moving on forward. I did plan to make the assignment for entropy and enthalpy due last Saturday. I obviously edited those. We didn't teach it. I didn't go through it, so I know you didn't know how to do it. I do have some empathy, and I did obviously change it. That's not fair. All right, moving on forward. Here we go. Define entropy and enthalpy. Please open up your guided notes. I have mine open. Please open up your guided notes. Today's the last day for the unit, so we're going to have to obviously turn this in after today. What happened through the unit? So as you find your guided notes, we talked about kinetics. We talked about different rates of reactions. We talked about effective collisions. What's an effective collision? It's oriented correctly with enough speed. What are 4 factors that affect rates of reaction? Their concentration, its temperature, its pressure on gases, and surface area affect rates of reaction. We know those. We talked about potential energy in terms of catalysts. We talked about all the different portions of potential energy diagrams. We talked about exothermic versus endothermic reactions. We took some time to draw these. Now you know why, because you see them all the time. You should know all the portions of an endothermic reaction. You should know where the heat is for an endothermic reaction as well. You should know what happens with the addition of a catalyst. We talked about exothermic reactions. Heat's on the right side, reactants higher than the products. We should know that. We talked about equilibrium. We talked about the rates of reaction being the same or equal. Equilibrium has to be a closed container. I did a few reactions throughout the unit. I did like the alpha toothpaste, did the whoosh bottle explosion. Took some magnesium, I burnt some magnesium as well. We talked about equilibrium in terms of solution equilibrium and phase equilibrium. Phase equilibrium is going to be on the flat interval from BC or DE. We talked about solution equilibrium being the point of saturation. Then we talked about stressing systems at equilibrium. We talked about Le Chatelier and what he did. He stressed out chemical reactions by changing concentration, changing temp, changing pressure on gases. Next up for today's class, I'm going to start off by changing my topic number. Last topic was topic 4B. I got rid of chemical reactions because we already did that throughout the year. I already got rid of balancing chemical reactions too. This is going to be topic number 5, enthalpy versus entropy. 2 E terms you should definitely be aware of. Please change that to topic number 5. Last topic for the unit. All right, here we go. Starting off this portion of class. Using your cell phone or Chromebook, whatever device you're using right now, differentiate or define enthalpy and entropy. Define both those terms. Yes, they have to be related to something in chemistry, so make it chemistry related. Find something that you could actually understand, because some of these terms you're really not going to understand. So please find a term that you can relate to and understand. So please, I'll give you about 5 minutes, give it to 12:30. Please define enthalpy and entropy. Please write them right there within the note packet. Again, define both terms. Entropy, enthalpy. It's got to be a chemistry term. Give it till 12:30. All right, please define enthalpy in the chat, what you found for enthalpy. I'll give you guys another minute to copy that down. Some really good definitions there. Okay, as you're copying them down, we're just going to read a couple definitions that people put in here already. Property of thermodynamic system defined as a sum of the system's internal energy and the product of its pressure and volume. So maybe you know it's talking about pressure, volume. Maybe you know what internal energy is. Maybe you know what thermodynamic system is. Good definition. It works. Heat content, another definition. Heat content in a system at constant pressure. Cool. This one I like a lot. Enthalpy is a tendency in nature to change to a lower energy. Very close to what the definition is going to be for chemistry class. Nice one. For this class, at least. Another answer is total energy, total amount of heat in a system, solved by internal energy plus product of the pressure and volume. Cool. So a lot of you guys are talking about heat, pressure, volume. Good stuff. I'm going to copy whatever your definition is, put it down in the notes. It's totally fine. I'm going to put what Leo put for a definition because I like it a lot. Leo's definition. Let's highlight it here. I'll see you in the house. Thanks, Leo. Leonardo. Enthalpy definition is a tendency in nature to change to a state of lower energy. So that's what Leonardo put. Good. You can put your definition. That's totally fine. Not a big deal. We'll redefine these as well. And I'm going to ask that you do the same thing for entropy. Please define entropy in the chat. What is entropy? Please define entropy. Entropy definition. Several answers here, several responses. Thank you. Measure of a system's thermal energy per unit of temperature that is unavailable in doing useful work. Okay. So thermal energy again. Several people are talking about. Oh, I like that one. Measure of the disorder or randomness on a system. Maybe you can relate to that one. I'm going to throw that definition here as well. So definition I'm going to go with is Tintin's measure of the disorder. A measure of the disorder. Whatever you have put in the definition is totally fine. Or randomness. I like that. Randomness of a system. So we'll definitely figure out the difference between enthalpy and entropy within this class. Not a ton of time, but we will have time to go through a small section of notes, watch a flick, and analyze examples on that. So thanks for playing that little game to start off today's class. Let's go through, watch a little flick on entropy, then we'll jump into the notes.
There's a concept that's crucial to chemistry and physics. It helps explain why physical processes go one way and not the other, why ice melts, why cream spreads in coffee, why air leaks out of a punctured tire. It's entropy, and it's notoriously difficult to wrap our heads around. Entropy is often described as a measurement of disorder. That's a convenient image, but it's unfortunately misleading. For example, which is more disordered, a cup of crushed ice or a glass of room temperature water? Most people would say the ice, but that actually has lower entropy. So here's another way of thinking about it, through probability. This may be trickier to understand, but take the time to internalize it and you'll have a much better understanding of entropy. Consider two small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed in the two solids and still have the same total energy in each. Each of these options is called a microstate. For 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates. Of course, there are other ways our 8 quanta of energy can be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that some of the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates. Entropy is a direct measure of each energy configuration's probability. What we see is that the energy configuration in which the energy is most spread out between the solids has the highest entropy. So, in a general sense, entropy can be thought of as a measurement of this energy spread. Low entropy means the energy is concentrated. High entropy means it's spread out. To see why entropy is useful for explaining spontaneous processes like hot objects cooling down, we need to look at a dynamic system where the energy moves. In reality, energy doesn't stay put. It continuously moves between neighboring bonds. As the energy moves, the energy configuration can change. Because of the distribution of microstates, there's a 21% chance that the system will later be in the configuration in which the energy is maximally spread out. There's a 13% chance that it'll return to its starting point, and an 8% chance that A will actually gain energy. Again, we see that because there are more ways to have dispersed energy and high entropy than concentrated energy, the energy tends to spread out. That's why if you put a hot object next to a cold one, the cold one will warm up and the hot one will cool down. But even in that example, there is an 8% chance that the hot object would get hotter. Why doesn't this ever happen in real life? It's all about the size of the system. Our hypothetical solids only had 6 bonds each. Let's scale the solids up to 6,000 bonds and 8,000 units of energy, and again start the system with 3/4 of the energy in A and 1/4 in B. Now we find that the chance of A spontaneously acquiring more energy is this tiny number. Familiar everyday objects have many, many times more particles than this. The chance of a hot object in the real world getting hotter is so absurdly small, it just never happens. Ice melts, cream mixes in, and tires deflate because these states have more dispersed energy than the originals. There's no mysterious force nudging the system towards higher entropy. It's just that higher entropy is always statistically more likely. That's why entropy has been called time's arrow. If energy has the opportunity to spread out, it will.
Those random particles of entropy. Let's figure out some more information about it. All right, moving on forward. Here we go. Let's finish up the notes, analyze some examples, and get out of here for today. So moving on forward, we're talking about enthalpy first. Again, thank you for those who define those terms to me. I was trying to send you a personal message. I didn't get to everybody, but thank you. Enthalpy is a tendency of nature to change to a state of lower energy. So moving on down to a lower energy level. So think about this. Something that has a high energy level. Maybe something's like at a high temperature. Collisions are really going really quick. Those collisions aren't going to last that long. They can't last forever. They're going to eventually want to go down to a lower, more calm, cooling energy level. It's kind of like you log on to the Zoom meeting with Mr. Brown, chemistry class. You're so excited to come to class. You're like, oh, yes, the best class of the day. That's how I feel every day. We're best class of the day. And then you're like really excited to figure out what's going to happen. You probably don't really care about the COVID numbers anymore, but then you're really excited what happens for chemistry class of the day, the best class. And then like we get to it and then you're just like, oh, we're back at it. You're just at ease. You feel good. You're just relaxed. Enthalpy. Kind of high, just cools on down just a little bit. Not too much. You're still excited. You're still motivated. But when that bell rings, you're like, oh, that's when you're like, it's over. I know that feeling. It happens to me all the time. I hate it. But anyways, with enthalpy of exothermic reactions, in exothermic reactions, reactions are going to move towards the lower energy state. Move towards the lower energy state. Think about an exothermic potential energy diagram. Goes to high, then it gets low. High energy to low energy level. You don't have to draw this in really quick. Potential energy diagram for exothermic reaction is going to look something like this. You have a high reactant and then a low product. Moves towards a lower energy state. Another thing about enthalpy, the term that they love to express on the reagents. Just asterisk this a couple times. This is a term that, well, I keep talking about the reagents. The term that they love to ask in New York State for testing, if you had a test, would be systems in nature tend to change towards lower energy, which someone said to me earlier, and more disorder. You guys told me about disorder was randomness of particles. For the examples, the exopaths, this might help you out a little bit more. That definition helps you out quite a bit. That's enthalpy. It's tendencies in nature to go from high to low. Calm back down. Entropy. Next term, entropy. Last section of notes for the unit is a measure of disorder on a system. Disorder or randomness of a system. Disorder, not really organized. With entropy, the greater the disorder, the greater the randomness. What does that even mean? I talk about a heating curve. Again, you don't have to draw this picture here, this curve. different curve, heating curve this time. There's a heating curve. In a heating curve, you have three different phases. You could have three different phases. You have a solid, you have a liquid, you have a gas. You have solid, liquid, and gas in a heating curve. Someone asked about when will I post the recordings of the other classes? They should be right after. All my classes should be up there in the Google Classroom page, right after the daily agenda thing. So, you guys ask me a question. I go off on tangents for a second. So the last class, there it is, from March 11th. March 11th. There's a recording of that class. This class was nothing to record because I just put assignment up because I was sick or I took the day off that day, sick that day, sorry. Wednesday, see that's Wednesday. So it really is all right here in the Google Classroom page. But anyways, with phases, a heating curve or cooling curve, within the phases, think about disorder or randomness of particles. We know that solid particles are going to look, we'll draw solid particles, liquid particles, and gas particles. We know solid particles are going to be really close to each other. They're right on top of each other. There's not much space. It's called a crystalline structure. Solid particles, metals on the periodic table should look better than this. Wow. A crystalline structure is going to look something like that, solid. Liquid particles, mercury and bromine, two liquids on the periodic table, will look something like that. Gases, they take the shape of the container, they spread on out, they're moving all over the place. If I ask you which one's the most random for positioning, if I said which one is, could you not predict where the particle will be? Gas particles are the most random. They're moving all over the place. The least random, most organized would be solid particles. So as you go from a solid to liquid, entropy, randomness increases. From a liquid to a gas, entropy increases as well. If you go in the opposite direction, if you go from a gas to a liquid, entropy decreases. Liquid to a solid, entropy decreases again. All right, so let's finish up these notes. Entropy, again, you didn't need that curve in there. The solid phase has less entropy. Than the liquid phase, which has less entropy than the gas. So solid has the lowest entropy, gas has the highest entropy. Randomness. And below this, I'm going to add another bullet here. Put increase in entropy. Solid to liquid to gas. A decrease in entropy is going to be the opposite manner. Gas to liquid to solid. They love talking about phases and the transition of phases in terms of entropy. And last bullet, generally the side of the equation with the greater number of molecules, the more molecules there are, has a greater randomness, has a greater entropy, has a greater disorder. like coming to Proctor before the pandemic. You come to Proctor before the pandemic, the halls could get pretty crazy. But if you come to Proctor when they open up with half the population or a fifth of the population, it's not going to be as crazy. The more particles you have, the more crazy it is. The more people you have in a volume, the more crazy it's going to be. You take some particles away, it's not going to be as crazy or random. And that is entropy, randomness of particles. All right, folks, that concludes the notes. You can share this with me. You can send it to me. Once you're done, again, this is going to be due on Saturday. The note packet is due on Saturday. Let's finish up class and go through some examples on entropy and enthalpy. We'll do this together. Guess I'll leave this open for us. So the examples come from the classroom page. Examples, entropy and enthalpy. Some of you guys emailed me about this. Said, hey, Mr. Brown, I can't do this. Yeah, I know. Sorry. Examples, here we go. Exit pass you'll have to do on your own, which actually next class I'll give you like 10 minutes to work on it. Number one, I'll wait for 5 responses. 1, which term defines as a measure of disorder on a system? Disorder on the system refers to what term, please? Please report your answer in the chat, record your answer in the chat. The sooner you guys respond, the quicker we'll go through this stuff. Disorder on a system we know is going to be entropy. Good. A lot of B's popping through. Entropy, randomness on system. Number 2, entropy is a measure of 3 for 3. Thank you. 5, 6, 6 for 6, 7, 9 for 9. Thank you for those responses. Quick responses. Entropy, disorder on a system. Those would have been Regis questions. Number 3, which reaction results as an increase in entropy? Which one's an increase in entropy? Okay, rolling through, thank you. Several A's for responses. In this situation, what are we looking for? We're just looking at the phases. This one's going from a liquid. A is going from a liquid to a gas. So I'm thinking about a heating curve. Look at that heating curve. Thinking about a heating curve, and I'm locating my liquid and my gas. Liquid, gas. So liquid to gas, particles are increasing randomness, definitely. Let's check another one out just to make sure. A gas to a liquid. Gas is here, liquid's here. That's decreasing randomness, entropy. Particles are going to be more organized. Next one, check out gas to gas, very gassy. Those are not changing phases, no change in entropy. And the last one is gassy as well. That one is not changing phases either. A is the best answer for number 3. 3's A. Next up, number 4, analyzing the question, which statement is true concerning the reaction of N, I'm scrolling down, N gas plus N gas yields N2 gas plus energy. Let's talk about this one. Energy's on the right side. We know energy's on the right. It's got to be an exothermic reaction. So you know energy's on the right. It's got to be exo. It's got to be releasing heat. So we're releasing heat. You guys could all analyze this equation and say, oh, N plus N come together to make one compound. It's forming a bond. You could say that. Hopefully you can notice it's forming a bond. Hopefully you can tell me the answer is going to be D. But anyways, if you forget anytime throughout the year, energy is released when you form a bond. Think about this example right here. So anyways, in an exothermic reaction, what happens? You have N plus N come together to form a bond. So what happens when they form a bond? These two smash. If they smash with the correct orientation, enough speed, it's going to form a bond. So when these two things smash together, N and N come together, they hit. What happens in that collision? is as they collide, it creates a little friction. So as they hit, friction happens, heat is released. Forming a bond, when two things come together, they hit, they collide, energy is released. Think about that situation when you form a bond. When you're breaking a bond, it's going to be the opposite manner. So breaking a bond, you have a compound, fixed proportion of two or more elements. When it breaks to two different elements, it's going to be absorbing heat. That's a common type of principle they ask a lot throughout the year. Exothermic reaction releases heat. It's not going to be C, it's not going to be A. You should be able to look at this and say, hey, it's forming a bond. 4, the best answer is going to be choice D. 4 is D. Number 5, which reaction tends to become less random as reactants form a product? Please put the answer in the chat. All right, rolling on through, thank you. We want less random situation. Again, I'm drawing my heating curve. Solid. Don't really worry about the gas to gas. Solid to gas. What happens here? Solid to gas increases randomness. A solid to gas is called sublimation. A solid to a gas increases randomness. A solid to gas is called sublimation. A solid to a gas, same trend, solid to gas. A solid to a gas is called sublimation. A big S word, big jump, sublimation. And let's check out the last one. Solid, gas, solid. So don't worry about the ones that are common. Look at the gas to solid. That's decreasing. A gas to solid is called deposition. That is decreasing entropy, less random. Particles are more arranged in that situation. That answer, best answer is going to be choice D. Number 6, try that one out. Which series of physical changes represents entropy increase during each change? Increase in randomness. There it is. Yes, Jubila. If it goes from solid to liquid, it's increasing. Increasing randomness, increasing number of particles that can be randomly disordered. This one right here, it's talking about increase in randomness. Increase in randomness, got to go from a solid liquid to a gas. Choice D is the best answer for number 6. A few more questions. 10 questions? All right, just trying to figure out the time frame. Number 7, which occurs when a sample of CO2 solid changes to CO2 gas? 7, please record your answer in the chat. Going from a solid to gas, what happens there? Sublimation. So a lot of us are going to be stuck with this order. Something's in great order and more order, it's organized. If it's less order, it's chaotic, randomly dispersed. Number 7, the best answer is going to be choice A. Greater randomness, entropy, less order. Not organized. 7, best answer is A. Nice job. Number 8, which changes in a sample of water is accompanied by the greatest randomness? Entropy. What do you think for 8? All right, cool. All right, so the first thing I highlighted were the phases. We have liquid to gas. Liquid to gas is definitely increasing. So that's the first one. It's definitely increasing. A gas to gas, there's no change in in phases. It's going to stay at the gas. That's equal. A solid to solid, again, that's staying stationary. It's not moving. Solid to solid, not moving. And the last one, a solid to liquid. Solid to liquid, solid liquid's going that little jump right there. That's increasing. The greatest increase, entropy, the greatest temperature, the greatest phase change, greatest randomness is going to happen within the gas phase. So temperature is greatest here, and the gas is going to be most disordered. 8 is A. 8 is A. A couple minutes left. Number 9, talking about enthalpy. That's the answer for enthalpy. Systems in nature. This is the definition for enthalpy. Systems in nature. I should copy that exact definition right there as well. Systems in nature tend to change towards lower energy and more randomness, more disorder. Low energy, like coming into chem class, you're excited, but then you have to reduce, and less disordered, less randomness. We know what we're doing in chemistry class. There's no surprises. I do the daily agenda for you. I go through the COVID numbers, all that stuff. Choice A is the best answer. And last one, talking about enthalpy again. What's the best answer for this? In terms of entropy and energy, systems in nature tend to undergo changes towards what? Think about it. This one got you a little bit, it looks like. Again, it's a term for enthalpy. Low energy, lower energy, more disordered, more random. More disordered, more random means higher entropy. Higher entropy for that. A few of you guys threw that in there. Number 10, the best answer is going to be choice C. All right, guys, at this point, you could do the exit pass, but tomorrow's class, I'll give you like 10 minutes to work on that as like a warm-up activity to give you time to do that in class. So you can do that now, you can do it later. It's up to you when you want to complete that. But that's it for today's class. Have a great day. Make a decision. Stay safe. See you next time. Sorry about your disorder is going to, your high of class is going to now be reduced. Enthalpy is going to really go out the door. Bye, guys. Have a great day.
Mr. Brown.
You too. See you, Frank. 8, number 8. Best answer was choice A. 8 was A. 8 was A. Bye, Cam. Bye, Nadina. Bye, John. Bye, Kai. Have a good day. You're welcome. See you guys.